Today's lecture is our fourth on imaging science. Let's look at the objectives for today. After today's lecture, students will be able to describe analog and digital representations of signals. Students will understand bit depth as it relates to contrast display and matrix size as it relates to spatial resolution. Students will know about picture archiving and communication systems networks and how images are stored and transferred. Let's start with the decimal system. In the decimal form, 10 digits 0 through 9 are used to represent numbers. The value of each digit in a number depends on its position in the row. For example, the number 1503 represents 1 times 10 to the power 3 plus 5 times 10 to the power 2 plus 0 times 10 to the power 1 plus 3 times 10 to the power 0. The leftmost digit is called the most significant digit, and the rightmost digit is called the least significant digit. Digital information can be represented as a discrete system of integers. If we use two integers, then we have a binary form. In binary form, two digits 0 and 1 are used to represent numbers. Digits 0 and 1 have the same meaning as in the decimal form. We can represent numbers greater than 1 by placing several digits in a row. The table on this slide shows how to count in binary form. Except for 0, we always start with 1 and then 0. This slide shows an example of how to convert from binary to decimal. When you hear the word decimal, think of analog, and when you hear the word binary, think of digital. So to convert from binary to decimal, you are going to multiply each binary digit by powers of 2 and add the results together. Essentially, you are expressing the binary form as a series based on powers of 2. To get the correct highest power, start your count from the right with 0 as the first and count from right to left. So let's go through this example. The number to convert is 1101. We count from the rightmost digit starting with 0. This gives us powers of 0, 1, 2, and 3. So that's 0, 1, 2, and 3. We then take the first digit, which is 1, and multiply that by 2 raised to the power 3. Add that to the second digit, which is 1, multiplied by 2 raised to the power 2. Add that to the third digit, which is 0, times 2 raised to the power 1. And finally, add it to the last digit, which is 1, times 2 raised to the power 0. The sum of all this is 13. Next, to convert from decimal to binary, you will divide by 2 until you are left with the number 1 in the numerator. The remainder values are the binary form. Let's go through this example. 14 is divided by 2 until a number less than 2 is obtained. The binary is the remainder digits written in order starting from the bottom as shown here. The binary for 14 is then 1110. The binary for 11 is 1011. And the binary for 42 is 101010. Currently, in nearly all radiological imaging systems, analog information from an image receptor is converted to digital form. The information is then processed, stored, and transferred in digital form. Finally, the information is converted back to analog form for image display systems. Let's look at analog representation of information. In analog form, information is represented by a physical quantity whose allowed values are continuous in space and time. There are an infinite number of possible values between the lower and upper limits of the representation. The figure on this slide is a continuously varying voltage signal. Suppose you want to convert this analog voltage signal to digital form, you will need to break the signal into discrete values. This is done by an analog to digital conversion system. In digital representation of information, the information is represented by a physical quantity that is allowed to have a limited number of discrete values at any moment in time. There are only a finite possibility of values between the lower and upper limits of the representation. If a portion of a discrete signal is limited to one of two values, it is called a binary digit or bit. One bit has two possible configurations, 0 or 1, or off or on. Digital information represented by binary digits can be encoded into capacitors. For example, if a capacitor is charged to a specific voltage, that is state 1. if the charge is below the specified voltage, that is state 0. So capacitors can be used as solid-state memories. On this slide, I show three continuous signals representing voltage pulses. Above the graph are digital representations of these voltage pulses that uses a sequence of 4 binary digits. In the previous slides, I spoke a lot about the binary digits of 0 and 1. A binary digit representing a 0 or 1 can only represent two values. To represent more than two values, several bits must be used. If 8 bits are used, that is called 1 byte. 2 bytes is one word. One word requires 16 bits to describe it. The capacity of a computer memory, a storage device, or a unit of storage media is usually described in kilobytes, megabytes, gigabytes, or terabytes as shown in the table on this slide. Note the differences between units used to describe computer memory capacity and digital information storage capacity. In our regular usage, a kilobyte will mean 1000 bytes because we usually count in base 10. In computer memory terms, because counting is done in base 2, the computer engineers settled on 2 raised to the power 10 because it gives the closest value to 1000, that is 1024. And it continues the same way with the other units. As we saw on the previous slide, computer memory and storage consist of bits. The amount of storage depends on the size of a word. Recall 8 bits is equal to 1 byte. For an 8-bit system, you can have 1 byte equal to 1 word. Also recall that each bit has one of two states and can represent the numbers 0 and 1. There are 2 raised to the power n possible configurations for n bits. The table on this slide shows different numbers of bits and the possible configurations based on that formula. For example, a 1-bit system is 2 raised to the power 1 and has 2 possible configurations for the numbers 0 and 1. These are the binary digits 0 and 1 as shown in the table. A 2-bit system has 4 possible configurations for numbers 0, 1, 2, and 3. These are the binary digits 00, 01, 10, and 11 as shown in the table. For example, an 8-bit ultrasound image system will have 2 raised to the power 8 or 256 possible grayscales, with 0 as black and 255 as white. Digital images are represented by a rectangular or square array of picture elements called pixels. Each pixel represents a single number, and the image is a matrix of these numbers. For example, in nuclear medicine, each pixel contains a count detected by a portion of the crystal of a scintillating camera. In CT, each pixel represents a property of the volume element or voxel in the patient. The number in each pixel is converted into a digital light intensity when displayed on a screen. On the previous slide, I talked about a rectangular or square array of picture elements called pixels. The display format of a monitor, that is the number of pixels per image, depends on the spatial resolution desired and the field of view. To detect objects as small as 1 mm spatial resolution in a fluoroscopy image, if the field of view is 23 centimeters, then a 512 by 512 matrix size will suffice. The spatial resolution in this case is 1.12 line pairs per millimeter as we calculated in a previous lecture. You can see that calculation on this slide again. Mammography requires even more pixels to accurately display image information. 4K displays refer to horizontal resolutions of around 4,000 pixels. For example, a monitor may have a rectangular array of 3840 by 2160 pixels. The importance of matrix size on image resolution is shown on this slide. Imaging modalities with higher spatial resolution and larger fields of view require more pixels per image so that the image format does not degrade the resolution. A digital chest image requires at least a 1024 by 1024 matrix to properly display the image. The images on this slide shows a chest image displayed in various formats. You can see the effect of the matrix on the image. In general, an image format should be selected so that the pixel size is less than 1/2 the size of the smallest object to be seen. We looked at matrix size on the previous slide. That was important for proper spatial resolution. Now let's look at bit depth and its effect on contrast resolution. Remember that each pixel represents a single number and the image is a matrix of these numbers. The largest number that can be stored in a pixel depends on the number of bits used for each byte. If 8 bits is equal to 1 byte, then using the formula 2 raised to the power n, we have 2 raised to the power 8, which is 256 possible numbers. The largest number stored is 2 raised to the power n minus 1, or 255, so the range of numbers goes from 0 to 255. The contrast resolution provided by an imaging modality determines the number of bits required per pixel. Imaging modalities with higher inherent contrast resolution require more bits per pixel or a higher bit depth. For example, MRI and CT have higher inherent contrast than ultrasound, so will require more bits per pixel to properly display all contrast levels. Ultrasound has limited contrast resolution, so 8 bits per pixel is enough to display all contrast levels. This slide shows you the effect of proper bit depth in an image. Image D has a bit depth of 1 because it uses 1 bit per pixel to display the image. 1 bit per pixel means 2 raised to the power 1, or 2 possible numbers per pixel, a 0 for black or a 1 for white. In this case, that means image D has pixels with 2 shades and can only display black and white. Image A shows a bit depth of 8, or 256 possible grayscale values. CT requires 12 bits per pixel because of the higher contrast resolution provided by CT images. 12 bits has 2 raised to the power 12 shades of gray, or 4096 possible shades of gray. There are two calculations on this slide. The first shows an example of the calculation needed to determine how much computer memory in bytes is needed to store an image. The important thing here is to recognize the structure of this formula. In the first calculation, metric size is a squared value in the numerator, so it will increase your memory needs by 4 if it is doubled from 512 to 1024 for the same bytes. For the same metric size, the number of bytes scales linearly. The second calculation shows that if you use the 1 byte system and a 512 by 512 matrix, you can store 228,000 images on a 60 gigabyte storage media. Again, if you look at the structure of this formula, this time metric size and bytes are in the denominator. So increasing them will reduce the number of images you can store, and decreasing them will increase the number of images stored. The matrix is squared, so doubling decreases the number of images stored by a factor of 4, and cutting in half increases the images stored by a factor of 4 for the same bytes. Let's look now at image storage and management in the next few slides. Acquired images are transferred and stored in computer networks. These computer networks are known by various names shown here. A common network is the Picture Archiving and Communication System, or PACS. The main components of computer networks are image acquisition computers, archiving systems, a central controller, a database manager, and a display station. The figure shows the network components and various topologies. Stored medical images are often transferred between computer networks. To allow images to be transferred easily, the ACR and NEMA came up with the DICOM standards. DICOM includes standards for the transfer of images and related information from individual patient studies between imaging devices and storage devices. DICOM specifies standard formats for images and other information being transferred, services that one device can request from another, and messages between devices. DICOM also provides standards, particularly the Grayscale Standard Display Function (GSDF), for the consistency and presentation of displayed images. We talked about the DICOM GSDF in the second lecture in this series. Of the various computer networks I mentioned 2 slides ago, the PACS is the most common implementation. PACS is a system for storage, transfer, and display of radiological images. PACS communicates with the Radiology Information System, Hospital Information System, and electronic medical records. The Radiology Information System is not always a separate system. It may be part of the Hospital Information System or incorporated into the PACS. The Radiology Information System commonly assigns an accession number to the patient that is used in PACS to identify the patient. Communication among the Radiology Information System, Hospital Information System, electronic medical record, and PACS is often implemented using a standard called HL7 or Health Level 7. This standard is used for the electronic exchange of alphanumeric medical information such as administrative information and clinical laboratory data. The amount of storage capacity required by a PACS archive depends upon the modality or modalities served by the PACS, on the workload, and the storage duration. This table gives some examples of storage sizes encountered in radiology imaging. Let's finish with image compression. Because of the large volume of imaging data generated daily in radiology departments, storage can be a challenge. Images are usually compressed before storage to save space. There are two categories of compression: reversible, also called lossless or recoverable compression, and irreversible, also called lossy or non-recoverable compression. In reversible compression, the uncompressed image is identical to the original. Typically, reversible compression provides compression ratios from about 2 to 3. In irreversible compression, information is lost, and so the uncompressed image will not exactly match the original image. However, irreversible compression permits much higher compression. Ratios of 15 to 1 or higher are possible with very little loss of image quality. Let's now answer a few questions. First question: if the number 16 in binary form is 10000, what is the number 17 in binary form? The correct answer is 10001. Next question. The calculation below shows approximately 228,512 by 512 images can be stored on a 60 GB disk if 8 bits is used per pixel. How many images can be stored if the image matrix is reduced to 256 by 256 for the same bytes? In this formula, because matrix size appears in the denominator and is a squared factor, cutting the matrix size in half when you go from 512 by 512 to 256 by 256 means that you can increase the number of images stored by a factor of 4. So the correct answer is 915,000. Next question. Suppose an imaging system that displays computer tomography images uses a 12-bit system. How many grayscale values can be displayed? The correct answer is 2 raised to the power 12 or 4096 shades of gray. This is the last slide. Thank you for watching this presentation.